Hi there, this is Simple Harmonic Motion, Lesson 6, Energy Conservation. So, recap question. So let's pause and have a go. A 3 kilogram mass is whirled around in a vertical circle on the end of a light string of length at 0.75 meters. At the top point of the circle, the speed of the mass is 6.8 meters per second. What is the tension in the string at this point? So, free body diagram. So we've got the tension acting down, we've got the weight acting down, and we've got the centripetal force mv squared over r acting down. So the equation, if they're all acting in the same direction, is sum of the forces mv squared over r. So the sum of the forces is T plus mg equals mv squared over r. So the tension is mv squared over r minus mg. Then factorise and put some numbers in. So tension it's going to be mv squared over r minus g. So numbers wise, m 0.3, got the bracket, 6.8 squared over the radius 0.75, and then we've got to minus 9.81. And that gives us a tension of, if you put that in your calculator, 15.6 newtons. Hopefully that went okay. Let's move on. So free oscillation. A freely oscillating object oscillates with a constant amplitude, and the total potential and kinetic energy of the object will remain constant. So at any point in time, the total energy system will be equal to the potential energy and the kinetic energy. I'll probably call that EK actually. Potential plus kinetic. And it occurs because there are no frictional forces acted on the object, such as air resistance. Obviously, this is a model, and in real life, this would not be the case, as any oscillating system would lose energy to the surroundings via heat and sound. So, energy variation. So, if you want to take some notes, just pause at any point. So, position 1, we've got maximum displacement. The potential energy will be a maximum. Kinetic energy will be 0. Total energy would remain constant at all times. Position 2, the total energy is a combination of the potential energy and the kinetic energy. Position 3, the potential energy will be equal to 0. This is the equilibrium position. And the total energy is still the total energy, it's still the same. The kinetic energy will be a maximum. Same as position 2. And then the other extreme, position 5, which is the same as position 1 at the maximum displacement. So we get a table like this. So in position 1, you've got maximum potential energy, 0 kinetic. Equilibrium position, you've got 0 potential, maximum kinetic. And at position 5 is the same as position 1. So if you want to pause and make some notes, feel free to do so. It's quite intuitive though, so it should be pretty straightforward. Let's do some questions. So if you want to pause and have a go at this one. A simple pendulum consists of a mass of 50 grams attached to the end of a thread of length 60 centimeters. Calculate the period of the pendulum. So let's do that first. So T equals 2 pi root L over G. Let's put some numbers in. So the time period is 2 pi root L, so we've got 60 centimeters, so 0.6 meters divided by 9.81. And if you calculate that, you should get 1.55 seconds. Then let's do part B. The maximum height reached by the mass if the mass's maximum speed is 1.2 meters per second. So what we need to use here is the conservation of energy. So kinetic energy to potential energy. So the loss of kinetic energy will be equal to the gain in potential energy. So the kinetic energy is half mv squared. So the loss of kinetic equals the gain in potential, which is mgh. So the masses cancel, so we just need to rearrange to find the height that it would go, the vertical height. So height is equal to v squared over 2g. So that's 1.2 squared divided by 2 times 9.81, which is 19.62. And that gives a height, maximum height of 0.073 meters. Hopefully that question went okay. Let's move on. So you want to pause and have a go at this. So a simple pendulum consists of a 25 gram mass tied to the end of a light string, 800 millimeters long. The mass is drawn to one side until it is 20 millimeters above its resting position, as shown on the diagram. When released, it swings with simple harmonic motion. Calculate the period of the pendulum. So let's do that first. So it's t equals 2 pi L over g. So the length is 0.8 meters for 800 millimeters divided by 9.81. So that gives a time period of 1.79 seconds. So that should be pretty straightforward. Then let's do part B. So part B, show that the initial amplitude of the oscillations is approximately 0.18 meters and the maximum speed of the mass during the first oscillation is about 0.63. So let's do the maximum speed first. So we can do the potential energy into kinetic energy. So we just need to do mgh equals half mv squared, cancel the m's, and then rearrange to get v. So v is equal to the square root of 2gh. You could use Suvats if you wish, you would get the same equation if you use the equations of motion. So the velocity is equal to, or the maximum speed, is equal to square root of 2 times 9.81 times the change in height, the 20 millimeters, so 20 times 10 to the minus 3. So that gives v equals 0.626 meters per second, which is approximately equal to the 0.63 meters per second, so that's okay. Then we need to calculate the amplitude, so I'm going to clear this again. Remember to pause or rewind at any point if you need to. So Vmax is equal to omega A. It's an equation that we've looked at previously in simple harmonic motion. So we calculated the time period earlier of 1.79 seconds, so we're going to use Vmax equals 2 pi over t, or 2 pi A over t. So to get the amplitude, it's Vmax times the time period divided by 2 pi. And that will give us A. So let's just put our numbers in. So the V from earlier, 0.626. If used as 0.63, it's okay. It's no big problem. Multiplied by the time period, which was 1.79, divided by 2 pi. And that will give the amplitude. And the amplitude is 0.178 meters, which is approximately equal to the 0.18 meters that was required. So hopefully that went okay. Let's look at the final part of this question. So let's pause and have a go at this. Remember to rewind if you need any of the information. So, calculate the magnitude of the tension of the string when the mass passes through the lowest point. So, just draw a free body diagram at the lowest point. So we've got the weight acting down, mg. We've got the tension going up, and the mv squared over r going up as well. So the sum of the forces is equal to mv squared over r. So the sum of the forces is T minus mg. sensible to take up as positive, as that's the direction that the mv squared over r is going. Then we just need to rearrange to find t. So t is equal to mv squared over r plus mg. So I'm going to factorise that as well. So v squared over r plus g. Then we just need to put some numbers in. So the tension is equal to the mass. The mass was 25 grams, so 25 times 10 to the minus 3. And then the speed was 0.626 squared, divided by the radius, which was 800 millimeters, so 0.8 meters, plus 9.81 for g. So if you calculate that, you'll get a tension equals 0.26 newtons, 0.26 newtons. And that's it finished. So hopefully you will either got all them correct, or now you know where you went wrong. Thanks for watching, and I'll speak to you soon.